Hey guys, welcome back to the channel. Today we'll be solving LeetCode 104, maximum depth of a binary tree. So we're given the root of a binary tree and we want to return its maximum depth. So what is the maximum depth of a binary tree? So in this case, it's going to be 3. So it's pretty much just how tall the tree is. So 3, if we look at 3 and we go down to 7 or 15, you can see that it branches down to 3 nodes, and this one only branches to 2, but we're looking for the maximum depth. So if one side is larger than the other, we're just going to return the larger side's length or maximum depth, and that is actually part of the solution. Maximum is a very important part of the solution. We need to remember that. We can solve this using a depth first search. So let's get into the explanation. This problem can be solved in 3 different ways. We can do a recursive depth first search, we can do an iterative depth first search, and we can do a iterative breadth first search. All of them solutions are going to have linear time complexity and linear space complexity. Um, well, the breadth first search solutions, the iterative ones, are going to be preferred in some cases, but I'm just going to go over the depth first search recursive because I think it is the easiest to implement and it helps people understand how trees work. So let's go over that right now. So basically, we're going to start at the root node. Our base case is just going to check, is this node null? If the node is null, we're going to return 0. So if our tree was just null straight off the bat, we could just return 0 and that would be correct. But if it's not null, we're going to add 1 to our return result, and then we're going to add the maximum of the left and right subtrees. So the maximum depth of the left and right subtree. So this is a sub problem. We're calculating the sub problem of the subtrees. So at 3, we're basically just going to add 1 like this, or we can just say 1, and then we're going to go down to the left node, and then we're going to reach here and we're going to add 1. Then we're going to try to go further, but we realize we can't, so we reach the end. And if we do ever try to go further, it's just going to return 0. And then we're going to try to go to the right subtree and we add 1, and we can see we can go further, so we go left and we add another 1. We try to go further and we realize we've reached the end, and even if we try to go here, we realize it's still 1. So the max, so this is also going to be a sub problem. It's going to calculate the max of the left and right, and it's going to realize the same, so it doesn't matter, it's still going to be 1. So now we're going to come upwards, we're going to start going upwards, and then this becomes 2, and then we go up again, and this becomes 3. We know it's going to become 3 because when this came back upwards, it's going to be 1. Now we're going to compare 1 and 2, and we're going to realize 2 is bigger, so we're going to add it to 1, and our final result is going to be 3, and we can pretty much just return after that. So like I said before, the time complexity is going to be O of n, and the space complexity is going to be O of n as well, because we're storing the recursive call stack, and the time complexity is O of n because we have to visit every node in the worst case. So let's get into our code. So the code for this problem is going to be very short. We won't even need a helper function. We can just do it in this function. So we're going to write our base case first. So if our root node is null, we're just going to return 0. And after that, we're going to we're going to return 1. And then we're going to add to it. We're going to add the left subtree. So we're going to call the max depth function again, and we're going to call it on the left subtree, so like this, and this is going to go all the way to our left subtree, and then we're going to do the same to our right subtree like this, and then we want to see which one of these returned a larger value. So we can use the max function in Python and compare them. And that's just going to choose the larger of the two and add it to our result. So at every specific node we get to, we're adding one. That's why this one is over here. If you want to store in variables and make it easier to see, then you can do that as well. But I'm just going to leave the code like this. And let's run it and see if it works. As you can see, it worked and it's pretty efficient. Thanks for watching, guys.